All right, let's take a look at dependent samples. These are a little trickier than what we've done on 9.1, 9.2, and 9.3. So the formula is for the t-score is d bar over the standard deviation of d divided by the square root of n. D bar is equal to the summation of d divided by n, where d is the difference. D is the difference from one to another. It's like a before and after kind of thing. And standard deviation, that's tricky to find. It's the n times the summation of d squared, the differences squared, minus the summation of all the differences quantity squared, all over n times n minus 1. And that's all under the square root sign. Assumptions that we make here: 1, samples are random, SRS. 2, they are dependent samples. So this is like the before and the after. This is you get on the scale, you take the diet pills for 6 months, so you get on the scale again. So you are like a dependent, it's dependent. N has to be less than 30, and it's got to be close to normal for any of these assumptions to be true. All right, so let's look at an example. A dietitian is trying to lower cholesterol. They set alpha at 10%. That's kind of high alpha. When it's usually people, it's low. It's 1% usually, or 0.5%. It isn't 10%. Okay, so there's 6 subjects. There's before and there's after. Let's roll out A, B, and C. Like A is what's the null and the alternative hypothesis. So the null hypothesis is no change. You took the diet things and there's no change. The alternative hypothesis is they're different. I would think we'd want it lower, but maybe it's good cholesterol. So they just said difference. They're just looking for a change one way or another. That makes it a two-tailed test, not a one-tailed, so a two-tailed test. And at the 10% significance level, n is equal to 6, and so degrees of freedom is 6 minus 1, which is 5. And so we look up our t-score on that chart again. Let me show you the chart. Here comes the chart. So we're looking at two-tailed test, 10%, two tails, 10% on the top there. And then we go down to 5 degrees of freedom. And so we're using 2.015. So that's on both ends because we looked it up as a two-tailed test. So they accounted for both pieces. So either this or negative that. Those are our cutoff points, our critical values. So sometimes instead of T there, you'll see a CV. That just stands for critical value. Our critical value has to, like our t-score, has to exceed 2.01 and or be lower than -2 points. So sometimes you'll see CV instead of T. Either one is fine, whichever one you like. All right, so we have our hypotheses, we have our pretty picture. Let's do our calculations. You got to do a lot of calculations on this one. So let me make a quick chart here. Before and after. So we got 210, 235, 208, 190, 172, 244. And then our after, we have, now this matched. So for the first subject, it was 210. They took the supplements and then took another test later, 190, 170, 210. Oh no, his went up, or hers went up. 188, 173, that one also went up, and 228. It looks like mostly they were lowered. So let's do before minus after. Before minus after. These are going to be basically the differences. That's D. So before minus after. This one minus that one is 20 and 65 and negative 2 and 2 and negative 1 and 16. And so it is important that you leave that before minus after is equal to this. So we can get negative values. That means it went up instead of down. We add all those together. I have a little total column here. So that's 100. Now we're going to do B minus A quantity squared. Usually we're doing that in statistics because we want to account for both positive moves, positive and negative. So by squaring it, it forces them all positive. 4,225, 4, 4, 1, and 256. And so if we add all of those up, we get 4,890. All right. So now let's find our D bar. That's our overall difference. So that's the summation of all the differences, which is 100 divided by how many there are. So 100 divided by 6. D bar counts as 16.6 repeating. All right. So now we're going to take that information and put it into, well, D bar will come into play, but when we're finding our t-score. So we're going to put a pin in that. We're going to use that when we have that. Let's find our standard deviation. So standard deviation is going to be this, n times the summation of d squared minus quantity summation of d, quantity squared rather, all over n times n minus 1. So we've got all of those calculated here. We have 6. We know that's 6. We did the summation of that. That's 4,890 minus, we did the summation of the difference. That's 100 quantity squared right there. And then times 6 and then times 5. 6 minus 1 is 5. So we got 30. So that is a standard deviation of, let's see, on the top, we get 19,340. On the bottom, we get 30. You do that again, that's the square root of 644.6 repeating. And that is about, we'll go to hundredths place, 25.39. All right, so now we can find, we've got S sub D, we've got D bar, we've got N. So now we can find our T statistic. So let's go over here, find our T statistic. So that will equal 16.6 repeating minus, well, nothing. So we don't have to have, that's just D bar on top, over 25.39 divided by the square root of 6. Now, actually putting these into this equation should look familiar, right? That's a standard deviation divided by the square root of the sample size, the error, right? Standard error. And the mean, more or less, the D bar is about the mean. Okay, so let's 0.608, that's about 1.61. Not enough. Look, here we go. That's the t-score is 1.61. We needed to have it exceed 2 or be less than negative 2 to be significant at the 10% level. And 10% was actually kind of high. So we failed to reject the null at 10% level. That means if we're failing to reject, this is our conclusion. We conclude that the mean before and the mean after are basically the same. The average cholesterol level is not significantly changed. You can just restate this, that the before mean and after mean are not significantly different. They are the same. Are not significantly different. All right. All right, awesome. Next video will be on 9596.